Hello and welcome back. Today we're going to review Unit 5, Sequences and Series. I'm going to break this review into two separate videos. Although it was a fairly short unit, I want to spend some good amount of time reviewing some of the specific topics. In this video, this first video, we'll look at what lessons we learned, and I'll briefly show you the Common Core standards associated with this unit. And then I'm going to ask you to take time to write down the formulas and then get to some topical reviews. In the next video, we'll start off with some topical reviews and then conclude with the summary of all the important things that you should be able to do from this unit. As a reminder, pause the video as we go through to write down anything that you need to. Here are the 6 lessons that we learned in this unit. The big focus was on arithmetic and geometric sequences and series, but we added in a little bit of summation notation as well as application problems dealing with mortgage payments. Here are the Common Core standards associated with this unit. Just take a moment now just to get a sense for them so you can kind of see the types of things you'll be asked to do on a Regents exam. So pause the video now and just get a sense for them. There are 4 major formulas that we had in this unit, 3 of which will be on the reference sheet. The one that will not be on the reference sheet is the arithmetic series formula. So make sure you make a note that you must memorize that one. The other ones are going to be given to you. To find the nth term in the arithmetic sequence, all you have to know is just the first term and the common difference. Because the formula is of the nth term is the first term plus n minus 1 times the common difference. That's the formula to find the nth term in an arithmetic sequence. Now it'll be helpful to make sure these formulas, as you write them down, are a nice handy place for you to look at and refer to as we go through this video, because I'm going to be referring to these formulas a lot. The series, which is just the sum of values in a sequence, for arithmetic is going to be taking the number of terms that you have in the sequence that you're adding together, multiplying it by the sum of the first and the last term in your sequence, divided by 2. Now your teacher might have written it in a different form, such as maybe n over 2, parentheses, a1 plus an. Okay, they're equivalents. There might be other equivalent forms as well, but both are acceptable. A geometric sequence, the nth term, is found by taking the first term and then multiplying by the common ratio raised to the n minus 1th power. And the geometric series formula is to be found using the formula taking the first term, multiplying by 1 minus the ratio to the nth power, divided by 1 minus the common ratio. Now for the geometric series, it's worth noting that on the Common Core reference sheet, it's written a little differently. It's written without the a1 factored out, without the first term factored out. So it's going to be written like this: a1 minus a1 times r to the n, divided by 1 minus r. They're equivalent. But it's important to note that those are the same formula, and this is the one that's on the reference sheet. Okay, pause the video and make sure you have these formulas in a handy location for you as we go through this video. There were 2 types of formulas that we had with sequences. One was called explicit, one was called recursive. The domain for sequences are always the positive integers. You'll never have fractions that aren't integers. So you'll never have 1/2 as an input. You'll never have negative numbers as an input. You'll never have 0 as an input. Okay, so the domain is going to be 1, 2, 3, 4, 5, dot, 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 It keeps going on forever and ever. Okay. And essentially the reason for that is because the domain is just really the placeholder of where you are in the sequence. The first term, the second term, the third term, the fourth term, and so forth. Okay. Because sequences are just a list of numbers. Explicit formulas are written in a way where you have just one equation, such that you can just plug in your n value. So if you want to find the 30th term, just plug in 30 for n, and it gives you the 30th term quickly. Okay. So it's something that you can easily evaluate to find the nth term. So some examples of explicit formulas are maybe an is equal to 3n plus 2. You can plug any value of n that you want, starting with 1, 2, 3, 4, to find out a certain term in the sequence. You might also see it using function notation, maybe f of n is equal to 3n plus 2. Those are examples of linear sequences. You could also have geometric sequences, so for instance 2 times 3 to the n minus 1, or you could have f of n is equal to 2 times 3 to the n minus 1. Okay, so if you can see it in both forms. The an is typical for sequences, but you should also recognize that it could be written as function notation. The recursive formula for a sequence has two parts. Must always have two parts. First, you need to indicate the first term or terms in the sequence. Because then you're going to write a rule that is used to find the next term based on previous terms. And the important thing to know here is that it's always based on previous terms, or just a term. Okay. So, for instance, you're always given the first term in a recursive. So let's say the first term ends up being 5. And I want my rule to be adds 2 to the previous term. Then I'm going to identify an as the previous term, which is an minus 1 plus 2. That is a recursive formula. Now just a little side note though, with recursive formulas you might see it written like this. A of n plus 1 is equal to a of n plus 2. I'm not really a fan of this way because it's not as intuitive in some respects, but you might see the second part, the rule part, written in either one of those forms. They mean exactly the same thing, it just starts off with n plus 1. You could also see it with function notation. So you could say, for instance, f of 1 is equal to, let's say, 7. And let's say I want the rule to be multiply each term by 5. Then I would determine the nth term as 5 times the previous term, which is going to be f of n minus 1. So explicit formulas, you just plug a value in and you get the term. Those are the nice ones, easy to work with. The recursive formula, you have to have two parts. First you define the first term, and then a rule to determine the next term based upon previous terms. Now just before we go on, I just want to indicate that you could have a couple starting terms. For instance, the Fibonacci sequence is a very common recursive sequence. Okay. Sequence of values based on a recursive formula. Whereas the first term is 1, the second term is 1, and then the nth term in the Fibonacci sequence is determined by taking the previous term, added to the term before that. Okay. So you get numbers like 1, 1. Add the previous two terms, 1 plus 1 is 2. Add the previous terms, you get 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 3 is 13, and so forth. That's the Fibonacci sequence, which occurs actually a lot in the real world and in nature. Another big topic in this unit was comparing the differences between an arithmetic versus a geometric sequence. Arithmetic is always a sequence of numbers that are formed by adding some value, adding the same value to each term to produce the next term. So an example would be, for instance, 2, 7, 12, 17, 22, and so forth. Notice that I'm adding 5 each time. You're adding the same number to get to the next term. The common difference is just that number you're adding. And the way you find it is if you know two consecutive numbers in your sequence, then you just take one number, subtract off a previous number. So I can do 7 minus 2, that gives you a 5. That's why it's called a common difference. It's found by subtracting 2, even though technically you're adding it to get to the next term. I could have chosen any two consecutive. I could have done 22 and 17. Notice that still gives me a 5. You just have to have two consecutive terms. A geometric sequence is a sequence of numbers formed by multiplying the same value to get to the next term. So a good example of that would be 1, 3, 9, 27, 81, ... What are we multiplying each time? Well, we're timesing by 3. Timesing by 3. The way we find the common ratio is if we're given any two consecutive integers, or numbers in the sequence, they're not always integers, I suppose, any two numbers in the sequence that are consecutive, you just divide by the previous term. So for instance, 3 divided by 1, that gives me the 3. Notice that's why it's called a common ratio, because you're dividing. If I chose the 81 and the 27, notice that gives me 3 as well. That's the common ratio. Now, an important thing to point out with the arithmetic sequences is that essentially there's a very close connection to linear functions. In the explicit formula, you always need to have the first term and then the common difference. So let's say I have the sequence of numbers 2, 7, 12, 2, 7, 12, 17, so forth. I want to write an explicit formula for that particular sequence of numbers. I'm going to take the first term, which is 2, and I'm going to add n minus 1 times the common difference. Okay, and that's the formula for that particular sequence of numbers. You could have also rewritten it as function notation. F of n is 2 plus n minus 1 times d, which is, in this case, 5, right? The common difference is 5. Now, if you really wanted to, if you want to get rid of those parentheses, you could technically multiply them out to give you 2n plus 2 plus 5n minus 5, and then combine it to become 5n minus 3. Okay. If you really wanted to, that's perfectly fine. There's no need to, though. And notice that's just a linear function. Okay. It's a very close connection to linear functions. The only difference here is that the inputs are only integers, positive integers. The recursive formula, because one thing you should be able to do is go between the a formula that's in explicit form to the recursive form. Okay. Remember, you have to define the first term. So the first term is 2. And then we're going to define the nth term. And with linear functions or arithmetic sequences, it's always going to be the previous term adding your common difference. So in this case, plus 5. There's your recursive formula. Note I could have used the A notation. So A1 is 2. A of n is equal to the previous term plus 5. Notice also I could have written A1 is 2 and AN plus 1 is equal to AN plus 5. Okay, those are all equivalent. But you should be able to very easily go between these two forms. Notice in this form, after you multiply it out, the common difference is always multiplied with the input. So in this case, the input is n. And in the recursive, you're always adding the common difference. So make sure to make a little note about that. For a geometric sequence, those are closely connected with exponential functions because you're multiplying by the same thing each time, by the common ratio. So let's go back to that example. We have 1, 3, 9, 27, and so forth. Okay. If I were to write an explicit formula for there, what I do is I write down the first term, which is 1, and I multiply it by the common ratio, which in this case is 3, raised to the n minus 1. And like before, I could also write this using function notation. So like f of n is going to be 1 times 3 to the n minus 1. In the recursive formula, again, we have to define the first term. So the first term is 1. And then the next term, the nth term, is found by taking the previous term times the common ratio. So it's 3 times the previous term. There's your recursive definition. Notice still you could have had the A notation. In a case it would look like this. And you could have also had the n plus 1 notation. So f of 1 is still 1, but f of n plus 1 is equal to 3 times f of n. Okay, all of these are equivalent. Note that in the explicit form, the base is your common ratio, and the recursive form, you're multiplying the previous term by that number. Okay, so just make sure that you notice that. Now, in a sequence of values, you might be asked to find the certain number in the term in the sequence. Okay, the 50th term, the 243rd term. Well, that's pretty far out there. The 50th term, for instance, in this sequence, and I tell you it's arithmetic, of 3, 9, 15, 21. So, it helps to write down the nth term formula for that sequence. So, the nth term is going to be found by taking the first, which is 3, adding n minus 1 times the common difference. Now you have to find that common difference. Remember, the common difference is found by taking any two consecutive numbers in the sequence and subtracting off by the previous number. So 9 minus 3 is 6. So this right here is the formula for that sequence to find the nth term. So if I want to find the 50th term, I just plug in 50 for n. So 3 Now the n minus 1 becomes a 49 times a 6. And if you do 49 times 6, that gives us 294. So 3 plus 294. Add the 3, 297. So that means that the 50th term in the sequence, 294. Notice I could have used my calculator, hit 3 plus 6, answer plus 6, answer plus 6. I could have done that to get to the 50th term. However, that's the last resort if you forget how to use this formula. Okay, you should be able to easily use the arithmetic sequence formula to find the nth term in a sequence of numbers. For a geometric sequence, we're going to use the geometric formula. To find the 8th term, we need to know the first term and the common ratio. So it helps to write down the formula for the nth term. So the first term is 64, and we have to find the common ratio. The ratio is always found by taking any two consecutive, I just end up choosing the first two, because usually the easiest ones to work with, any two consecutive terms in the sequence and dividing them by the previous one. So 96 divided by 64, and if you type that in your calculator, that gives you 1.5. Or 3/2, depending on how you want to apply it. Okay. 1.5 is a nice decimal, so I'm going to use a 1.5. And it's going to be raised to the n minus 1. That is the formula to find the nth term. So if I want to know the 8th term, I'm going to plug in 8 for n. So it's 64 times 1.5 to the 7th power, because 8 minus 1 is 7. Type that in your calculator. That gives you 1,093.5. That's going to be the 8th term in that sequence. Now note, finding the nth term in the sequence is much easier to do with the explicit formulas, which we just did. With the recursive formulas, sometimes you're given a recursive definition. Let's say we have the function, the first value of the sequence is 2, and the recursive rule is take 2 times the previous minus 3. Okay. To find the, let's say, what is the 4th term? Let's say that's the question it's asking. What's the 4th term in the sequence? You can't just plug in 4 with a recursive formula, because recursive is always based upon the previous term. Okay. So what you have to do is you have to find all the consecutive terms from the first all the way up to what you're looking for. So f of 1 we know is 2. F of 2, here's where we have to use the rule. 2 times the previous minus 3. So 2 times the 2 here minus 3. 4 minus 3 gives you 1. Now you can look for the 3rd term. F of 3 is going to be 2 times the previous minus 3. So 2 times the 1 minus the 3. 2 minus 3, that gives you negative 1. Now I can find the 4th term, because it's based upon that 3rd term. 2 times the previous, which is negative 1, minus 3. Negative 2 minus 3, negative 5. Okay. So for recursive, you have to actually find all consecutive terms. So f of 4 is negative 5. Okay, so I'm going to end the video here. We're going to continue the reviews in the next video. In the second video, we will look at finding the equations of sequences giving non-consecutive terms and what to do there. We'll look at the summation notation, then get into some series work, and then some more series work with defining writing the notation in summation, writing the sum of a series using summation notation. We'll look at the applications of mortgage payments, and then finally we will sum up the important things in this unit. Thank you for watching, and I'll see you in the next video.